So when G is 0, it counts in the order 0, 1, 2, 3. And when G is 1, it counts in the order 0, 2, 1, 3. And it's repeating, so it'd be, this first one be 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and so forth. It's a 2-bit counter, so what that means is if G equals 0, then I would get as my outputs 0, 0. My next output would be 0, 1. My next output would be 1, 0. My next output would be 1, 1. And then my next output would be 0, 0. And it would count in this order if G was 0. If G was 1, then I would go, my first output would be our outputs 0, 0. And then I would have 2, which is 1, 0. And then 1, which is 0, 1. And then 3, which is 1, 1. And then it would go back to 0, 0. And then 1, 0, and so forth. So it depends on what G is as to what your next state is. And this one, it's pretty easy to come up with your states and some good names for the states. So, because there's 4 of them and they're numbers, so I'm gonna call them A, B, C, D, but state A really represents 1. State B is 2. State C is 3. And state D is 4. And these are each represented by, oh, well, wait, that's, sorry, 0, we start with 0. State A is 0, state B is 1, state C is 2, state D is 3. And those will be the 2-bit numbers 0, 0, 0, 1, 1, 0, and 1, 1. So construct a state diagram or state table. So I did a state diagram. So I'm starting with state A. Now my output is 0, 0. So my output turns out to be the same as my state name. That's handy. And depending on what G is, if G is 0, then my next state would be B, which is 0, 1, if G is 0. Now, if G is 1, then my next state is state C, which is 1, 0. Because when G is 1, we go from 0 to 1, 0. Now, if I'm at state B, if G is 0, my next state is C, it's 1, 0. And if I'm in state B, which is 0, 1, and G is 1, then my next state is 1, 1. If I'm in state C, which is 1, 0, and G is 0, then my next state is 1, 1. And if I'm in state 1, 0, and G is 1, then my next state is 0, 1. And if I am in state 1, 1, doesn't matter what G is, I'm going back to 0, and so I can just put a 1 there, just because that's always going to happen. So construct a state diagram or state table. I did. Specify a state assignment. I did that right here. Construct the state assigned table. So present state, next state. What was our input? G equals 0, G equals 1. Output and let's call the outputs, did they have names for the outputs? W, Z, I guess. So present state, we have 0, 0, 0, 1, 1, 0, 1, 1. And if G was 0, it just went to the next state. And if G was 1, it followed a different path. 0, 1, 0, 0 went to 1, 0. 0, 1 went to 1, 1. 1, 0 went to 0, 1. And 1, 1 went to 0, 0. And our output looked just like our name of our state because it was handy because they were numbers. Okay, let's call this, I did y2 and y1 again. So y2, y1, except it looks like I did it backwards order this time. y2, this is capital Y2, capital Y1, capital Y2, capital Y1. So let's do y2. And it depends on little y2, little y1, and G. And when G is 0, that's this first row, present state is 0, 0. I'm doing just y2, that's my first column here. So it'd be 0. And when its present state is 0, 1, that's 1. When it's 1, 1, it's 0. When it's 1, 0, it's 1. And when G is 1, when it's 0, 0, I have a 1. When it's 0, 1, I have a 1. And for the other two, I have zeros. And so I have y2 equals, this top little circle here is y2, y1 bar, g bar, plus this column here is y2 bar, y1, and this little circle is, let's see, y2 is 0, and g is 1. And then to get y1, this is our second column. And in this first group here that corresponds to G equals 0, that's the first row of my Carnot map. So that's a 1 and a 0 and a 0 and a 1. And on our, for G equals 1, I have a 0, a 1, a 0, and a 1. Yes. So that gets me this group, this little guy all by himself, and then these two ones. So y1 equals, this one single one all by itself is y2 bar y1 g plus the column is y2, y1 bar, plus this group going across here is, let's see, so y1 is 0, so that's y1 bar, and g is 0, so that's g bar. And then our output is handy because it's identical to our present state. So you can just say w equals y2 and z equals y1. And so the output is easy. Questions on that one?
You said our next bit says in order y2, y1. How do you know that? How do you know it's y2, y1, not y1, y2?
Oh, there's no rule. You can call it whatever you want.
You just call it that?
Yeah, unless there's instructions that are given.
You would just have to match it up with the present state? Like you would just, if you said,
Yeah,
oh, okay.
yeah.
I thought,
And I guess you only know if they give you like a very loud kind of thing.
Yes.
They just declare it from
so
present.
if they give you the, yeah.
Right. Right. Typically, so there are the reason why it's different is that there are some systems where the most significant bit is on the right, and there's some systems where the most significant bit is on the left. So like if you're looking at a number in our everyday numbers, this is the most significant bit and this is the least significant bit. So this would be 0, 1, 2, 3. But not all systems are like that, and some are the other way. And so it's just, some people are used to working with one and others with the other. And I'm just used to counting 1, 2, 3. So I count a lot of times in the direction. This is most common, but I don't always do it that way.